Problem 3.11. In this problem, we have a copper tubing which is joined to a solar collector plate of thickness T. The working fluid maintains the temperature of the plate above the tube at T0. There is a uniform net radiation at the top of the plate, and it is also being exposed to a fluid, therefore it has convection. The bottom part of the plate is completely insulated. Using this information, we need to derive the differential equation that governs the temperature distribution in this plate. We also need to obtain the solution to the differential equation for appropriate boundary conditions. We're going to take this problem to be steady, one-dimensional, with uniform radiation, uniform constants, and we are going to assume that the temperature at the bottom is equal to the temperature of the fluid. If we look at the schematic, we see that the three modes of heat transfer are present on this problem. We have conduction, convection, and radiation. Let's look at each one of them independently. We have conduction going in, which is simply Qx, defined by Furrer's law. We simply said that is negative K T T dx. Please note that all the modes of heat transfer are defined per unit length. That's why we define them as Q prime. The amount of conduction Lavine is going to be Qx plus delta x prime is going to be equal how much it entered plus the change that it had in the space dx. We could define the change that we have for radiation as simply the amount of flux that we have for radiation times the value of the length dx. Therefore, we could simply say that this value, since it's a constant, times the value of dx. If we do the same process for the convection, we simply said that is the value of the flux due to convection times the distance dx. We define the flux due to convection to be h, the t at the position we're looking for, and t infinity. And then once again we multiply it by dx to get Q prime. If we look at the schematic, we could see that the three modes of heat transfer are present in the problem. Notice also that the three modes are defined per unit length, therefore they are defined as Q prime. For conduction, using Furrer's law, we simply said that it is going to be negative K T dt dx, where lowercase t is the thickness. The conduction Lavine, the plate, is going to be simply whatever the amount that entered plus the change that it had in the distance dx. The amount of radiation change is given as the amount of flux, which is a constant value, times the distance that it travels, dx. And the change in convection, once again, is going to be the flux due to convection times the distance dx. Using Newton's Coulomb law, we see that this is T minus T infinity times dx. If we do a balance of energies, we could simply say that the conduction going in plus the change of radiation going in has to be equal to the amount of convection Lavine plus the amount of conduction Lavine. If we replace all these terms into this equation and we simplify it a bit, we find that it's going to be KT, the second, minus H, T minus T infinity, plus the flux of radiation. Notice that at this moment, this equation is not homogeneous, due to the fact of having this minus t infinity. We're going to use the assumption that theta is equal to t minus t infinity, and we're going to substitute this equation. Therefore, what we get is the second theta dx squared minus h over kt. We divide all the terms by kt. This is theta plus the flux of radiation divided by kt. This is now a homogeneous second-order differential equation with a constant coefficient and a source term. The next step is to see how we solve this differential equation. The solution for this type of equation is going to be theta is equal to C1 e to the lambda x plus C2 e to the negative lambda x plus s divided by lambda 2 to the second power. The value of s is the source term, which in our case is equal to the flux of radiation divided by kt. Lambda is the constant coefficient, which is equal to square root of h over kt. Let's now define the boundary conditions. These two conditions are provided at two different values of x. Notice that we have that at x is equal to 0, the temperature is constant, and it has a value of T0 or T0. We also see that there is the same temperature at the value of 2L. We also notice that we have exactly the same conditions at the top and at the bottom of the plate. Therefore, we could say that in terms of the temperature distribution along x, the temperature has to be symmetrical about x is equal to L. And as we did before, when something is symmetrical about a particular position, we could assume that the boundary condition for that location is simply insulated. Let's represent those boundary conditions numerically. At x is equal to 0, t is equal to t0. Therefore, we could simply say that at theta equals 0, it's going to be theta 0, which is basically t0 minus t infinity. And then we could say that at x is equal to L, the flux that we're going to have is going to be 0. In terms of data, we could simply say theta dx is equal to 0. Let's now apply the boundary conditions into the governing equation for the temperature. We find that theta naught, which is the evaluation of temperature at x is equal to 0, is equal to C1 plus C2 plus S divided by lambda squared. For the second boundary condition, we need to determine the derivative of theta with respect to x, which is going to be equal to C1 lambda e to the lambda x minus C2 lambda e to minus lambda x. Applying this into the boundary condition, then we simply say that at negative k, the theta dx, which is minus k, c1 lambda e to the lambda L minus c2 lambda e to the lambda L is going to be equal to 0. Notice that this evaluation of lambda takes place at x is equal to L. By doing those evaluations, notice that we have two equations and two unknowns. The two unknowns are going to be C1 and C2. The values of C1 is simply going to be theta 0 minus S over lambda squared divided by 1 plus e to the 2 lambda L. C2 is going to be theta 0 minus S over lambda squared divided by 1 plus e to the negative 2 lambda L. If we substitute back into the original equation, we find that the value of theta is going to be theta 0 minus lambda s over lambda squared times e lambda x divided 1 plus e 2 lambda L plus e minus lambda x divided 1 plus e minus 2 lambda L plus s theta squared. To recap, this is the solution of a plate exposed to radiation and convection at the top and insulation at the bottom. We take the fact of using the three modes of heat transfer to evaluate the differential equation and the temperature distribution along this plate. The boundary conditions that we use are going to be constant temperature at value of x is equal to 0, and we use the symmetry of the problem to evaluate insulation at x is equal to L. After we evaluate the boundary conditions, we find the constants C1 and C2, and this is the final temperature distribution for this particular problem. Please make sure to go back and understand carefully what is the difference between the balance of energies that we have in order to obtain the differential equations, how to solve it, how to apply the boundary conditions, and how to get the value of theta or the temperature as a function of x.